Hello students, today we are going to have lecture number 16 in the series of lectures on classical mechanics. In the previous lecture, we have seen the Hamilton's equation of motion, and we have also seen some important conclusions and the importance of the Hamiltonian formulation itself. The point that I expressed in the last class is that Hamiltonian formulation has a better physical insight into the dynamical system when compared to the Lagrangian formalism. So in today's class, we will see how it gives you more physical insight. And we will also see how the algebraic structure is evolving in the Hamiltonian mechanics, which is going to be very useful in the future formulation of the mechanics corresponding to the quantum case. That means I am trying to explain you how the Hamiltonian mechanics is going to be very helpful in moving from classical mechanics to the quantum mechanics. Whereas the Lagrangian dynamics or the Lagrangian formulation itself is not going to directly help you to make such a kind of smooth transition to the quantum mechanical case. And therefore, because of these reasons, it is considered that the Hamiltonian formalism is considered to be better in terms of physical understanding of a dynamical system. One of the first reasons that you can observe in the case of the Hamiltonian formalism is that the Hamiltonian, when you are going to write down, is a function of q, p, t. So this is how we have already seen this detail, whereas the Lagrangian is going to be a function of q, dot, t. So the difference is there here, where the q dot is converted to the p. And the conversion, or we say the transformation of q dot to the p is what is known as the Legendre transformation. So that is very important. And here you have to be very careful that you will sometimes get a doubt that q dot is there, which is basically representing the velocity of a particle. Then suppose if you multiply by the mass, then mass times the velocity should give you the momentum p. So a simple multiplication of mass will make a conversion from the q dot to the p. So that is what you initially think. But it is not so. This is not always true. So it is not always true, especially in the case of variable mass problem. So when the variable mass is going to be taking place, then the time derivative of the mass will be entering into picture. So you can't just multiply by mass at any given instant of time. Okay, so that is where the problem comes. That means at a time t1, then the mass at time t1 multiplied by the q dot at a time t1. Okay, at a time t1 is what I am writing in this suffix here, at a time t1. So then this is what is the momentum at a time t1. So we'll say that pt1 I will write down. Okay. If you are, this is okay, not this is notation is not very important, but for understanding, I'm writing like this. You can write down p of t1. So whether you write it like a suffix or inside bracket, that is fine. The meaning is the momentum at time t1. That is what I mean to say. So everywhere you have to write down time t1. At a later time, you'll have to represent like this: the mass at time t2 multiplied by q dot at time t2. So everything should be taken at time t2. That will give you the momentum at time t2. So you see that this kind of a simple multiplication with a constant mass is not true all the time, because you'll have to consider certain dynamical system that changes its mass. So therefore, we need a suitable transformation to make a conversion from the q dot variable to the p. Okay, and that transformation happens to be the Legendre transformation. And the transformation is very crucial, because it is not only just q is converting to p. So this is not the only transformation. Together with L has to be converted to H. So this is very important. When q dot is making a transformation to the p, at the simultaneously what is happening is that the Lagrangian is getting converted to the Hamiltonian. So the process takes place together. So this is the exact thing that we have discussed in the last two classes. So because of this transformation, what happened is that we have obtained the set of equations, and the set of equations is known as the Hamilton's equation of motion. And they are given by the time derivative of the q. Okay, that means evolution of q is equal to dou h divided by dou p, and then we have p dot is equal to the negative of the partial derivative of Hamiltonian with respect to the q. So this is the equation that we have established in the last class, and these equations were given the name Hamilton's equation of motion. So you remember them right now because we have discussed more in detail about the derivation itself. And the most important point is that there is a negative sign in the expression for the p dot. And one of the important physical concept that is coming into picture is that once you know the Hamiltonian of the system, that means given h is given h for a particular dynamical system, then how the dynamical variables q and p will evolve. That is called q dot. Q dot means how q will evolve with respect to time. P dot means how p will evolve with respect to time. So they are given by the partial derivatives of the Hamiltonian. That means if the Hamiltonian is available to you, you can easily evaluate the partial derivative and then tell how the dynamics is going to take place. So in this way, the Hamiltonian formalism gives you a better physical insight when compared to the Lagrange equation of motion. You have written the second order Lagrange equation of motion, but however, directly from that equation, you will be unable to make some kind of better interpretation about the dynamics. You only close your eyes and then mathematically solve the differential equation, namely the Lagrange equation, and then plot the solution and then understand it. But here it is not so. Here you understand that the moment Hamiltonian is available to you, then their partial derivatives will give you how the position and the momentum will change with time. That is called a dot. How these things will change with the time. So therefore, Hamiltonian of a dynamical system is more meaningful than the Lagrangian of the system. Okay, and in fact, Hamiltonian itself is coming from the Lagrangian, that's fine. But our understanding is it is better to make this transformation from Lagrangian to Hamiltonian and then make use of the Hamiltonian to understand the dynamics better. This is one of the main conclusions that we made in the last class. And now what is that you'll have to note down further for understanding is that you'll have to note down the standard configuration, namely that when you write the h is a function of q, p, t, the standard meaning is, without even when we are not specifying, the meaning is very natural that it is a function of all q's. That means it is a function of q1, q2, etc., qn, where n is the number of degrees of freedom, then comma, then this p represent p1, p2, etc., pn, then at last you'll be having possibly time. So time may be explicitly present, and in some systems it may not be present, but in the most general situation when time is also present, we write like this. So the important point is that whether you write q1, q2, etc. or not, it means that all possible number of degrees of freedom are included in the system. So this has to go without saying. Only then you can understand further details about the Hamilton's equation of motion, namely 1 and 2. So by that, what I mean to say is that because of this particular implied statement, the meaning is like this. When I write q dot here, it means that you'll have to write down the equation for every one of the degrees of freedom, which means that q is nothing but q1, q2, q3. Therefore, this equation has to be written for every one of the degrees of freedom. Therefore, I will have to write down that q1 dot will be equal to dou h divided by dou p1. This is important, q1, p1. And not only that, comma, then you have, this is one equation. Then the second equation would be, I'll write down that q2 dot will be equal to dou h divided by dou p2. And this has to be repeated for all the number of degrees of freedom. And if you are going to have capital N among them, then we will be writing like this, qn dot will be equal to dou h divided by dou pn. So this will be the set of all equations corresponding to the q dots. And not only that, and then corresponding to the second equation, we have the p dots. So therefore, we'll have to write down p1 dot will be equal to, I hope you are able to follow from the equation, this equation. I am talking about this one now. Okay, so this p dot equal to, so that's what I'm writing, p1 dot equal to negative of dou h divided by dou q1 dot, sorry, okay, negative of dou h by dou q1. Then the second one, p2 dot will be equal to minus dou h divided by dou q2 and so on. And the last one would be equal to pn dot is equal to minus dou h by dou qn. So how many equations are there? You'll have to count. So this is 1, 2, 3, 4, etc. n number of equation. Then this is n plus 1th equation. This is n plus 2, n plus 3, etc. Then we have n plus n. So if you count the number of equation that you have written till now, we have 2n equations are there. Right? So total number of equations is 2n equations of motion. So that means when we are saying the Hamilton's equation of motion, you should clearly understand that we have 2n number of equations of motion, each one of them being first order in time. This is important. When we write like this, in this particular style, when you write, you don't feel 2n of them. You only think that there is only 2 of them. So this kind of implied meaning should be clear to you. And it is also very important because several times the summation will come into picture. And you should know from where the summation is coming. The summation is coming because of the existence of several Q's and several P's. Okay, so whether you explicitly say this or not, there are several Q's and several P's are there, and the number of P's and Q's is equal to the number of degrees of freedom. If you are going to talk about a single degree of freedom, then fine, there is only one Q and there is only one P. That is fine. So you will have to specifically express this particular point so that it will be clear for you to understand further. So this is first important point that it has a 2n number of equation of motion, which means that, so this is another important conclusion, which means that in the 2n, that this is what is important, in the 2n phase space, or we say dimensional, in the 2n dimensional phase space, the manifolds are given by their solutions. So manifold means curve. I already explained you what is meant by manifold. In the case of the simple 3-dimensional Euclidean geometry, you use the word curve. When you are moving to higher mathematical space, higher dimensional mathematical space, the word curve is replaced by the word manifold. So that's all about it. And when you are going to solve this 2n number of equations of motion, then their solutions will give you trajectories, and these trajectories are known as manifolds. So where are the manifolds are going to be drawn? That you'll have to draw it in the phase space, and the phase space itself is 2n dimensional. Why phase space is 2n dimensional? That is already there here. It's clearly visible. That phase space, what is phase space is the set of all variables from here to here. From here to here, this is the phase space. So if you are going to plot here, if you are going to plot all the Q's along the x-axis and all the P's along the y-axis, that particular diagram is known as the phase space. And therefore, let me write down first phase space. Okay, so if you are going to draw between Q's and P's, then total number of axes that are required to draw will be 2n. That is what we mean to say 2n dimensional. Okay, if you have 2 axes, then it is 2 dimension. If you draw 3 axes, 3 dimension, etc. So you'll have to draw n number of axes for Q and additional n number of axes for P. So total number of axes that you are going to draw will be n plus n. So 2n number of axes that you are going to draw in mathematical space. Remember, drawing is in mathematical space, so don't worry about visualization. And if you do that, that is known as the 2n dimensional phase space. In that phase space, you are going to draw the solution trajectories. Solution trajectory means the solution to this equation. This is your Hamilton's equation of motion, and you are going to solve them, and then the solution, you are going to plot it in the phase space, and they are known as the manifolds. So the manifolds are going to be drawn in the 2n dimensional phase space. So this is the first point that should be clear to you when you are talking about the solution to the system. Now here comes an important point. Let me explain now the concept. If you are going to consider a simple geometry, that means within the Euclidean space, so that you can easily understand. So let me now draw some diagram in the three-dimensional Euclidean space. So I have drawn a plane here as an example. So this particular plane, you can write down that this is XY plane, because so this can be an X here and that can be a Y. If you are going to choose like that, then this plane that you have drawn here is the XY plane. And it is clear that this is a two-dimensional plane. And now suppose if I am going to draw, or suppose if I am going to bring another plane, okay, which is perpendicular to this. It is not necessary that it has to be perpendicular. So let me draw some, let me bring some plane for you and then draw it like that. Okay, so this is another plane, and then I am going to bring it and then cut this. So what is the diagram? It should be clear. I have one horizontal plane, which is the XY plane, and now I am bringing another plane. Possibly this could be a YZ plane, because this vertical direction could be Z-axis. So in that case, we may say that this is a YZ plane. If you have names, it is not compulsory that you should bring a YZ plane. You can bring any plane making some angle. So that's fine. Now the point to be noted here is that if you are going to bring a plane like this, then there is an intersection. Intersection means one plane is cutting the other plane. So once the two planes are intersecting and then cutting here, so what is left out here? So what is the region of cut? So this is the place where the two planes will cut each other, and therefore after cutting, what is remaining? That is the question. So after the two planes intersect, what is the resultant? What is the conclusion? So that we have, so after intersection, I'll write down here, after intersection, we have a line. This is the point to be noted. So you can easily visualize, right? You have one plane is there. If you bring another plane and cut it, then what is the resultant object, which is the intersection of the two planes? Answer is the intersection of the two planes is a straight line. That's the answer. So we would like to write in a more general manner. If you start with a two-dimensional system, because plane, right? We start with a 2D plane. Therefore, I say that it is two-dimensional system. And if you are going to bring a particular surface and then cut it, you need not bring a plane only, but you bring any other. You can also bring a circular disc and cut. Okay, you can bring any other shape and then cut the plane. So that is the point to be noted. So if you start with a two-dimensional plane and then cut the plane with a constant surface, so this is a constant surface. So you bring a constant surface plane and then cut it, then it becomes a line. So this line is a one-dimensional object. That is what I am trying to explain. So this concept should be important. If you start with a two-dimensional object, and when the intersection is taking place, then the resultant object will be a two-dimensional object. This is very important. And if you repeat this procedure once again means, suppose if I bring another plane and cut it, okay, maybe I'll bring another plane, I'll draw it in another color. For example, I'll draw a plane like this. Okay, so that's a plane in blue color I'm drawing. And apparently, so this particular plane now in blue color shade is now going to cut once again the resultant object. The resultant object is already a straight line and it is making a cut. So you ask the question, what is the resultant of the intersection of the three planes? So question is clear. What is the resultant of the intersection of three planes? The answer is given by the blue color dot. You get a dot. Now there is no line. After the third plane comes and cuts the first two planes, then our final conclusion is that we will be having a point. Okay, so that will go to a point. So I'll say that this is a point which is nothing but zero dimensional. This is important. So we are interested in number of dimensions. So what happens is you start with a certain geometry. you make the intersection of another object, then what happens is, if you are going to start with n number of dimensionality, where the number of dimension is n, then after the intersection it becomes n minus 1. And when another plane comes and intersect once again, this becomes n minus 2. So our conclusion is, every time you bring a constant surface and allow it to intersect, then the resultant object will be having the number of dimensions given by 1 reduced every time. That is the conclusion. So n becomes n minus 1, n minus 1 becomes n minus 2, and you can't do anything further because it's already 0. Okay, so anything if it cuts more than that, and again it has to be a point only. So that's the meaning. So this is the last place where you'll have to stop the intersection, because it has already become 0-dimensional situation. So this point is clear that that we are discussing from starting from plane. So this is an example. You need not do this experiment with a plane only. You can also do the experiment with a case of sphere. For example, if you have if you imagine that you have a sphere like that, okay, and then you bring a plane like this and then cut this particular sphere. Okay, if you have a sphere is 3-dimensional, and bring a plane and cut. Remember, you don't have to bring all the time plane. You can bring any other surface also you can bring. But plane is easy to visualize. You can at least imagine what is happening. Okay, for that reason I am bringing the plane. So now you bring one plane and then cut it. Then once you cut the sphere using a plane, what is the resultant object? Resultant object means what is the resultant of the intersection of a plane and a sphere? That is the question. The answer is, it is going to be a circular disk. Isn't it? So circular disk will be the resultant object because of the intersection of a plane and a solid sphere. Sphere means you can assume solid sphere. So then you will be having a circular disk. What is the dimensionality of a circular disk is? Circular disk is 2-dimensional object. Now, so circular disk is something like 1 rupee coin. Now you have 1 rupee coin like object, and now another plane comes and cuts this particular 1 rupee coin like disk. Then what will happen is, you will get a line. So line will be the resultant object if you are going to perform one more intersection. Okay, and therefore the line is a 1-dimensional object. And when you have a line, you bring another constant level surface and then cut the line. Then what is the resultant of the intersection of line with the constant level surface is, you get a point. And therefore the point will be 0-dimensional in nature. So it's very clear, right? So start with the 3-dimension, 2-dimension, 1-dimension, 0-dimension, and you can't go further about it. So our answer is, or our idea is clear, that whenever you start with n as the number of dimensions, dimensionality of the system, then n will go to n minus 1, n minus will go to n minus 3, and so on until 0. So the idea is clear that this will keep on reducing 1 by 1 until it reaches 0. So this concept, when it is clear in the case of the 3-dimensional Euclidean space, you will now be in a position to visualize the phase space and what is happening in the phase space. Okay, so that is what I am trying to say here. Now, in the case of the phase space, you see here, in the case of the phase space, what is the mathematical dimensionality of the phase space? Phase space is 2n-dimensional. Okay, therefore, you'll have to start with 2n as the dimensionality. So the same expression you'll have to write down, that what in the case of the phase space, what is going to happen? Phase space, constant surface intersections. There's a title, phase space, constant surface intersection. So phase space is actually 2n-dimensional mathematical space. And if one constant surface is coming and if it is going to cut the surface there, then the resultant object will be having 2n minus 1. So 2n minus 1 will be the dimensionality of the intersection between the constant level surface and the original 2n dimensional phase space. And if you are going to bring one more one more level surface and make the intersection, then we will be having 2n minus 2, etc. And every time 1, 1, 1 will reduce, and ultimately this goes to 0. That is what is the meaning. So each one of this arrow which I have shown here, this particular arrow shows the process of intersection. Okay, so it is the intersection by a level surface. Level surface means something like a plane. Not necessarily it's a plane. It is something which remains constant. That's what I mean to say by a level surface. Okay. In the simplest case of the three-dimensional Euclidean space, a plane happens to be a level surface. But it is not necessary. Okay. A plane doesn't mean that it has to be rectangular in shape. Okay. It has to be in any shape. Okay. But it should be restricted in a plane. That's what it means. When you take a 1 rupee coin, it is circular in shape, but it is also plane. So you can now understand that rectangular surface is not required. It can be a circular surface also, but it is a planar object. So that is the meaning of level surface. So whenever you bring a level surface and then allow to make the intersection of the 2n number of manifolds that are present in the system, then the remaining, what is the resultant is that we will be having 2n minus 1. So the geometry is something that you will have to now understand what I am trying to say. So here you see that in the 2n dimensional phase space, you have the manifolds. Okay, manifolds means, the set of complicated curves that you are going to have in the 2n dimensional space. And in that particular system of curves that you have, you are going to make a cut, and the cut is made by something which is going to be a level surface. So if you are going to do that, then the resultant object will be having only 2n minus 1 dimensionality. So the number of dimensions will reduce. And if you discover another surface, if you discover another level surface and then make a similar intersection, then the number of dimensions will reduce, and then it goes keep on reducing like this. So this is what is happening mathematically or geometrically, whatever it is. So that's fine. Now, how do you understand it physically? So this is where I said that the Hamiltonian formalism has a better physical insight. So what is the physical insight corresponding to this kind of geometrical happening is that the level surface that we are going to have keep here is nothing but constant of the motion. So in the last class, I already explained the word constant of the motion has different names. Namely, it is also known as a conserved quantity. So physically conserved quantity. So either you write it by the name constant of the motion, or we can also say that it is a conserved quantity. Mathematically, we say that it is a simple constant. That's all about it. So that is, you simply say, mathematically, you simply say constant. The word of the motion, okay, of the motion that we write because dynamics is taking place. Otherwise, mathematically speaking, it's just a constant. When you draw, suppose when you draw a plane like this, then what is the equation of the plane means? We say z equal to 2 plane. What do you mean by that? So what do you mean by that is that if in the case of the z-axis, if this is the z-axis that you are going to have, and then if you are going to have the x-axis and then the y-axis, that is the origin. If this is origin, so this is x direction, y direction, then this is z-axis. So that will be z equal to 1, and this point will be equal to z equal to 2. So this is z equal to 2. So the entire plane, in the entire plane, the value of the z will be equal to 2. In the entire plane. That is why we say that z equal to 2 plane. So what do you understand is that there is a number 2 which remains constant throughout the plane. That is what we mean to say constant. That is what we say it is level. Level means you don't go down and you don't climb up, etc. No ups and downs are there. Constant means that is the meaning. That is why geometrically we also use the word level surface. Level surface means something remains constant, so there is no gradient to go up and down, etc. That's why it's called a level surface. So mathematically, a constant is called the constant of the motion, and physically we can understand that such a quantity is a conserved quantity as the dynamics is taking place. So this is the interpretation. Geometrical interpretation is or can be translated in terms of physical understanding. So that means in case if you are able to successfully discover one constant of the motion, then the number of dimensions or the dimensionality of the manifold comes down. That's the meaning. Originally, you have 2n dimensional manifold was there. Then, if you have discovered one constant of the motion, then the resultant dimensionality of the manifold is 2n minus 1. And in case if you discover another constant of the motion, then the dimensionality will reduce further, and it keeps reducing like this. So that is the conclusion. So our conclusion is very important, that every time you discover one constant of the motion, then the dimensionality of the intersection of the manifolds keeps on reducing one by one, and it can reach to the minimum value of 0. Okay, typically it will reach the value 1, because 1 is the place where you don't you have at least 1 degrees of freedom to move. 0 means it's a point, right? There is nothing to change. Therefore 0 is something that is not suitable for dynamics. So 0 is something which is fixed, static. Okay, a point means you can't move any side. At least line should be there for movement. Okay, and therefore this is now clear that our concept of the intersection of the plane is equivalent to determining or finding the constant of the motion for a given system, for a given physical system. So this is the first point to be noted. Second point to be noted here is that in the usual three-dimensional Euclidean space, the word surface is used. Surface means what? Surface of the sphere, surface of the cylinder, surface of a plane. So this particular diagram that I have drawn here, for example, this one, we will say that it is a surface of the plane. So the word surface is used as long as we are working in the three-dimensional Euclidean space. But suppose if you are going to a higher dimensional mathematical space, especially the 2n dimensional phase space, the word surface is going to be replaced by another name called hypersurface. So when you see the word hypersurface, you should not think that something you can't understand. It is not so. Whatever was the surface in the case of the three-dimensional system, the same thing is now called hypersurface, because it is something that you are unable to see directly. Okay, you can't see how it looks like, whether it looks like a bowl, or it is looking like the surface of the cylinder, or whether it looks like a planar surface. Like that you can't see, you can't visualize it, because it's mathematical object, and therefore the word hypersurface is used. So the clarity should be therefore should be clear to you. So what do you mean by that is that when you are going to have 2n dimensional phase space and then take a level surface, so instead of saying level surface, we say that constant of the motion hypersurface. You now get the connection between this. When you're talking about the constant of the motion, in which dimension you are going to talk about? In the higher dimensional mathematical space. Therefore, instead of saying that it is a constant of the motion, geometrically it represents. Geometrically means in the higher dimension, once again, geometry is known as topology. Therefore, in the language of the topological situation, the surface is replaced by the word hypersurface. Therefore, the hypersurface representing the constant of the motion, when it intersects the manifold, then the total number of dimension is reduced by 1. And like this, you can keep on reducing until it reaches 1. Okay, 0 is not required. 0 is for the static situation. Therefore, until it reaches 1. That means maybe here itself I will write down that we are not interested in going up to 0 here. So we can stop here when it is 1. So when that is happening, then you can count how many number of constant of the motions are there. Now you can ask the question, from 2n to 2n minus 1, how many constant of the motion? 1 should be there. then only minus 1 can come, right? And similarly, when you discover another constant of the motion, then it becomes 2n minus 2. So you have discovered 2 constants of the motion in the process, then 3 constants of the motion. How many constants of the motion should you discover in order to get a 1? So final answer should be 1. If it is the case, how many times you will have to perform the intersection? So that is quite easy. Now you can easily tell that in order to achieve the finally only one number of degrees of freedom, then we say that we will have to discover 2n minus 1 constants of the motion. Constant of the motion means level hypersurface. Geometrical language is hypersurface. 2n minus 1 hypersurface we will have to discover. Then what will happen? Then each one of them will reduce the number of dimensions, and ultimately it will reach to n equal to 1. Okay, so therefore why 2n minus 1 should be there? Is that clear? See, if you are going to start with the 7 degrees of freedom, then 7 will become 6, 6 will become 5, 5 will become 4, then 3, then 2, then 1. How many are there? You count. So this is 1. This is the one intersection. I am putting 1 tick. This is another intersection. So second tick. Third intersection. Fourth intersection. Fifth intersection. Sixth intersection. How many ticks are there? 1, 2, 3, 4, 5, 6. So 6 number of ticks I have put. 1 tick represents 1 constant of the motion. Therefore, if you want to reduce a 7-dimensional system to the 1-dimensional system, there are 6 number of intersections has to be done. Each intersection represents 1 constant of the motion. So if you have 7 dimensions, then 6 intersections should be done. If you have 2n number of dimensions for the case of the phase space, 2n minus 1 hypersurfaces are required. Therefore, there will be 2n minus 1 number of constant of the motion. So we'll have to discover 2n minus 1 for complete solution. Complete solution to the dynamical system. So this is the interpretation, physical interpretation. How do you understand or how do you visualize the physics of the problem from the geometry? So that point I have explained now. Now it is very clear. Now we will see one more technical term here corresponding to this. So let me explain that. So total number is the 2n minus 1. That is what I mean to say. So this is called maximal. Okay. So let me write down here the important terminology. If we can discover, or if we are able to, discover or find 2n minus 1 constant of the motion, then that particular dynamical system is said to be maximally superintegrable. So the terminology is very important. That's why I am writing. Actually, I can explain without writing anything. But however, you'll have to catch what I am speaking. Therefore, it will be better if you can spend 1 minute and then write down. Okay. So the point is this: if you are able to discover or find successfully 2n minus 1 constant of the motion for a given dynamical system, then we say that such a dynamical system is maximally superintegrable. Okay, because there is a maximum that is possible. Integrable means finding the solution. Superintegrable means you are able to find every one of the constant of the motion. Okay, you are able to successfully discover all the constant of the motion that is possible. So that is why it is known as maximally superintegrable dynamical system. So this is the first important terminology in the language of topology, okay, or whatever the classical mechanics that we are going to study within that terminology. So this particular definition is important. But remember that discovering 2n minus 1, that is a maximum number, is not always possible. It's not possible. So we will be happy if we can at least discover n among them. So for example, therefore, let us write down the second definition. If if we can discover more than n constant of the motion. You know what is n, right? First of all, you should know what is n. N is the number of degrees of freedom. If n is the number of degrees of freedom, then only 2n will be the dimensionality of the phase space. So that clarity should be there. And in that particular situation, suppose if you are able to discover n number of constant of the motion of the system, then that particular dynamical system is said to be superintegrable. So the difference between the previous statement and this statement is the previous one talks about the maximal, or we say that maximal condition or maximally superintegrable. Now we are going to say it is just superintegrable. So just superintegrable means you are able to discover totally n number of constant of the motion. So these are the important terminology that is required in order to distinguish the normal dynamical system, which is just integrable. Then certain systems will be just superintegrable, and there are only some special cases which are maximally superintegrable. So that distinction should be clear, and the distinction comes from the ability to discover the number of constants of the motion for a given problem. For a given problem means for a given Hamiltonian. That's the meaning. If you have a dynamical system, you should have a corresponding Hamiltonian. So once you know the Hamiltonian, for that Hamiltonian you should be in a position to discover them. Okay, so these are the two important points about the terminology. Then the third situation corresponds to the case where if we can only find less than n number of constants of the motion, then the system is non-integrable. So this is the requirement. So as you see that n number of constant of the motion apparently is very much necessary in order to say that a particular system is solvable. Okay, solvable is a simple English term, and in classical mechanics we use the word integrable. So integrability of the dynamical system. So if you are able to only find less than n number of constants of the motion, then we say that the system or the Hamiltonian system is non-integrable. In case if you are able to discover more than n of them, then it is superintegrable. Then sometimes you may get a doubt. Here it is more than n. Let me explain that. See, here I have written more than n number of constant of the motion. Here I have written less than n number of constant of the motion. So you may get a doubt what happens if it is exactly equal to n. Sometimes the doubt will come. So I'll therefore write down this particular point. So if exactly n number of constants of the motions are found, then what it is referred to as is, then it is the necessary and sufficient condition for the integrability of the dynamical system. So it is better that this kind of doubt may come, and now it is clear that if you are able to at least find n of them exactly, then we say that okay, it is you have reached the necessary condition and the sufficient condition for the integrability of the dynamical system. That means at least it has escaped from the difficulty of non-integrable system. Okay. Non-integrable system means unsolvable problem. So that is the meaning. From the difficulty of the unsolvable problem, you have entered into the regime where we say that the problem is solvable. That is what it means to say, if you are able to discover n number of the constant of motion. So this is the terminology. This is how we can visualize the geometry that is happening in the phase space and the physical insight that we can think about. And we will discuss more about the constant of the motion, because especially if you remember the last class work, we made one important statement. So what is that statement is that if the Hamiltonian of the dynamical system does not contain time explicitly, then it is guaranteed that every autonomous system is, for every autonomous system, the Hamiltonian is a constant of motion. This statement we made it in the last class, which means that, what is the meaning? The meaning is that you, without doing any mathematics or without doing any work, only if you know the Hamiltonian alone, then immediately you can say that Hamiltonian itself is a constant of the motion. That is the meaning. No, so every time I am now using the word, so you have to be careful. Here, every time I am saying that if you are able to discover, so which means that you'll have to put your effort to discover some constant of the motion. The conclusion that we made in the last class is that without doing any work, directly you say that the given Hamiltonian itself is a constant of the motion. So that is really interesting, right? So which means that out of the 2n minus 1 or whatever that number that you'll have to find, one of them is readily available. That is the statement that we made it in the last class, and therefore I think I have already explained that particular point, that given Hamiltonian itself is a constant of the motion, provided that it is not explicitly depending on time. So that point is already explained, and for many of the system, Hamiltonian doesn't contain time, so therefore it is a meaningful statement. So whenever Hamiltonian doesn't contain time, then Hamiltonian itself is a constant of the motion, which means that you are discovering one constant of the motion without doing any effort, and therefore we say that Hamiltonian is the first constant of the motion. So why do you use the word first is because now you'll have to discover additional constant of the motion by doing something. Okay, without doing anything, you directly say that Hamiltonian itself is the constant of the motion. Therefore, you say that out of the maximum number of 2n minus 1 constants of the motion, the one constant of the motion is already or readily discovered, and that is the Hamiltonian. And therefore, we say that Hamiltonian is the first constant of the motion. Therefore, your job is therefore to find what is the second constant of the motion, third constant of the motion, and so on until maximum of 2n minus 1 is reached. Okay, reaching 2n minus 1 is not easy, as I already explained. If you are able to find only less than n of them, then the system is non-integrable. If you are able to successfully discover n of them, then we say that okay, it is a solvable problem, because you are going to the situation where we say that it is a necessary and sufficient condition for the integrability of the system. So at least you must be able to discover n of them. In some rare situations and also some interesting situations, we will be able to discover all the 2n minus 1 of them. In such a situation, we say that the physical system is maximally superintegrable. So these are the points to be noted in terms of geometrical interpretation and physical meaning. We will see now the question comes automatically. Okay, first constant of the motion is Hamiltonian itself. And now the question is how to find. So this is the next important question. Then how to find additional constants of the motion. So you can now understand what do you mean by additional, because Hamiltonian itself is one constant of the motion. Anything that you are going to discover is going to be second constant of the motion, third one, etc. Of course, the order is not important. Okay, the first one happens to be naturally Hamiltonian, therefore we use the word first. Okay, if you are going to discover the z component of the angular momentum and x component of the linear momentum or constant of the motion, then you don't have to tell which one is the second and which one is the third. That ordering is not important. Okay, the first one is gaining the importance because it naturally evolves that it happens to be a constant of the motion. The ordering is not important, it's only the total count is important. So the question is therefore clear that if this is the situation, in order to say that a particular dynamical system to be integrable, at least you'll have to find out n number of constant of the motion for integrability. One of them is already available, which is Hamiltonian. Question is how to find the second, third, etc. What is the idea? At least you should have an idea on how to determine the constant of the motion. Okay, so that's what we are going to see. Okay, probably we will see that in the next lecture.